Hello everyone and welcome back to the channel. In system design, you will constantly hear terms like concurrent users and parallel processing. These concepts are crucial for building high-performance, scalable systems, but their definitions are often confused. While related, concurrency and parallelism are distinct ideas that highlight different aspects of your system handles work. Understanding this difference is absolutely fundamental for any system design interview. Today we are diving deep into these concepts. Okay, so let's get started to the heart of it. So with a simple example, let's assume that we have a kitchen, and let's start with concurrency. So concurrency is about dealing with many things at once. Imagine like a single chef juggling multiple dishes in the kitchen. They might chop vegetables for one dish, then stir a sauce for another, then check an oven for the third. They are rapidly switching between tasks, making progress on all of them, but not truly doing them all at the same time. Okay? On the other hand, parallelism, like it's about doing many things at the same time. So now imagine that you have multiple chefs in the kitchen, each working simultaneously on a different dish, or even different parts of the same complex dish. They are truly executing their tasks at the very same instance. It's about simultaneous execution. Okay? So it's a pretty easy. Like let's say that we have task 1, we have task 2, we have task 3, and concurrency, we will do them one by one, and that's it. It's pretty easy to understand. So the definition of concurrency is the ability of a system to manage multiple tasks or processing them in such a way that they appear to be running simultaneously, even if they are actually being executed in an interleaved fashion or a single processing unit, like a single CPU core. The mechanism that handles that, one single CPU core concurrency is achieved through rapid context switching. The operating system or runtime quickly switch between different tasks, giving each silence of CPU time. This rapid switching makes it seems like all tasks are processing at once from a human perspective. A good example for that, I guess, if you know Node.js. Node.js has a single-threaded web server, and it has something called event loop. It can handle thousands of concurrent client connections. It doesn't process them all simultaneously, but efficiently manage their I/O operations, context switching between connections that are ready to send and receive data while another are waiting. In desktop application, I guess you can type in a document while music plays in the background and a file downloads. Your single CPU might be rapidly switching between these tasks. Okay, so it's basically our processor might do this and go and after that do this, maybe go back and go back, something like that. Like you switch between tasks. Okay, so what are parallelism? Parallelism, it's exactly the opposite. Like let's say that we have 2-1 and task 2, and our CPU is doing both of them in the same time. So parallelism is actually simultaneous execution of multiple tasks or computations. This inherently requires multiple independent processing units capable of executing instructions at this exact same moment. These processing units can be multiple CPU cores within a single machine, multiple CPUs, or even entirely separate machines in a distributed system. The mechanism of this one, tasks truly run at exact same instant on a different cores or machines. This can be achieved with like multi-threading, like running multiple threads at on a multi-core CPU, or maybe multi-processing, like running multiple separate processing on a single machine or across machines. Example for that, I guess if you have a video rendering application, uses all 8 cores of your CPU to process different frames simultaneously, dramatically reducing total rendering time, something like that example. The goal of this one, the primary goal of parallelism, is to reduce the total execution time for computationally intensive tasks. It's about doing more work faster, okay? The trade-offs of parallelism, it's introduce overhead related to inter-process communication, data synchronization across multiple units, and significantly increase complexity in managing distributed state and ensure consistency. Okay, so when to use which in system design? So I would say you use concurrency when your tasks are largely I/O bound, like waiting for network, disk, or external services. You use it also when you want to improve system responsiveness and throughput without necessarily needing more hardware. Also, if you're dealing with a single machine that needs to handle many simultaneous connections. On the other hand, you can use parallelism when your tasks are CPU bound, like involve a heavy computation, or maybe you need significantly reduce the total execution time of a task, or maybe you have multiple processing units available, like multiple CPU cores and multiple machines. Okay, so I would say most complex systems utilize both, like a single server might use concurrency, which is like an event loop in Node.js, to manage thousands of incoming clients connections. And then for specific CPU intensive processing of those requests, it might spin up a worker thread that run in parallel on different CPUs. So yeah, So how to discuss this in system design review? So in system design review, when discussing how your system handles load, clearly define and differentiate these terms, like justify why you would choose one over another based on the nature of the workload, connections connected to specific architectural patterns. For example, our web servers will handle concurrency using an event loop, while our background processing workers will leverage parallelism across multiple machines for CPU-bound tasks, things like that. So yeah, concurrency and parallelism are not interchangeable, but they complete each other. Mastering these distinctions allow you to precisely articulate how your system manages work. So that's it for this video, and see you in the future.